Hi everybody, welcome to the next lecture on audio coding. Today about quantization and coding methods. So far we saw the analysis filter bank and the synthesis filter bank and the decoding side. And today we want to talk about the following block, the quantization and coding. And here you can see this is also controlled by this perceptual model, which we will talk about later. Yeah, so what's the objective? We want to have somehow a good representation of our spectral data coming out of our analysis filter bank. So we want to represent it compact with a low bit rate, because that's the goal of audio coding, right? And we also want to have the smallest possible perceptible distortion, which means despite the low bit rate, we want to have a high decoded quality after decoding. So this should be a high subjective quality, which means it should sound good to the human ear, which is different from, say, measuring the mean squared error, as we will see. So today we will talk about mainly this quantization and somewhat about noiseless coding, which we call entropy coding. So here you can see the different terms. We have the signal to noise ratio, which is just mentioned. This is basically measuring the distortion between original and decoded. So when we have an original, we take the decoded, take the difference, and then we have the distance between the two, but this can be plus or minus, so we square it. And then we can take the average, and then we get the signal to noise ratio. So this is easy to compute, but this does not allow prediction about the quality because our ear works differently. So that's why we have also the noise to mask ratio. So here in the picture you can see, here we have the signal energy. So here you can see horizontally the so-called coda bands. Basically these are our subband samples. And here vertically you have the dB axis, which is basically the energy. And you can see here, this should be your signal. So this is just symbolizing your signal. So it has this step here in energy. And down here you have the distortion. So this is what you get when you take the difference between decoded and original and square it and then compute the dB of it. This is the distortion, the power of the noise in dB. So this should usually be much lower than the energy of the signal itself, because we want to have a high quality. So ideally this should be as low as possible, such that the ear cannot hear this noise, such that this noise is hidden by the signal itself, right? So it needs to be much weaker than the signal. So this distance in SNR is the ratio in powers, and this is the signal to noise ratio here in dB. So you can just take the difference here, and that's the dB number for the SNR. Then we also have this so-called masking threshold, which is what our psychoacoustic model will produce, which we will see. So this tells us the sensitivity of the ear for the different frequencies or the different coda bands. So the coda bands are basically encoding different regions of the spectrum differently. So here's the first region, here's the next region, and so on. So the ear has different sensitivities for the different coda bands, and that's why this masking threshold changes. It also depends on the signal energy. So when you have higher energy, this masking threshold goes up, because the ear has these masking properties. So if a signal is louder, then the noise can also be louder before you can hear it. So when you then take the distance or the difference between the signal energy and the masking threshold, you get the noise to mask ratio, NMR. So this tells us how much headroom we have between the masking threshold and the signal energy. So this is actually where we don't want to have any noise, because this one would be audible. Anything above the masking threshold becomes audible. Anything below the masking threshold is inaudible. Right, so here we can see the distortion is below the masking threshold, and that's why in this case it's inaudible. Right. Yeah, so what I just mentioned here is actually the signal to mask ratio here, this part, relation between the signal and masking threshold. And this gives indication of the bit demand, because the noise is caused by the quantization. When we have less precise quantization with larger quantization step sizes, that means the distortion goes up. But it also means we need fewer bits. Right, so the higher we can make this distortion, the fewer the bits, the lower the bit demand will become. So when we have a high SMR, the high signal to mask ratio, that means the distortion needs to be low. That means we need more bits, or vice versa. If the signal to mask ratio is small, then the distortion can be higher, and we need fewer bits. Yeah, and then there's also this noise to mask ratio, which is this distance between the masking threshold and the distortion here. So this is the ratio of distortion with respect to the masking threshold, and determines the audibility of distortions. Right, it should be as small as possible, but smaller than 0 dB. So you want to have the noise below the masking threshold. Right, if it's below, then the distortion is inaudible, but if it's above, then it's audible. Right, so you want to have negative numbers here. Okay. So then to the quantization, right? So first we want to have a data reduction by removing irrelevance. And irrelevance means we lose information, but hopefully information that the receiver cannot detect, so in our case the ear, and that's why it's called irrelevance. We want to have explicit control of the quantization distortion according to the time frequency dependent masking threshold in the perceptual coder. So this is what comes out of our psychoacoustic model. And that means we also have high variability in local signal to noise ratio, depending on the signal. So it can be between, for instance, 0 dB and bigger than 30 dB. So 0 dB is, for instance, when you have noise in your audio signal, then the ear is not very sensitive to additional noise. And 30 dB is the case when you have tones, sinusoids, clean sinusoids. Yeah, and the most popular case for quantization is the scalar quantization. So here you can see it, and this is the simple case of a uniform quantization. This is used, for instance, in MPEG 1 or 2, layer 1 and 2, in the older A-track, and in AC3. And it means that the average distortion is independent on the size of the coefficients or the signal. Right? We have a quantization step size which is constant. So maybe I should call this, instead of coefficient of the signal. Okay. Yeah, so here you can see it. We have an input signal X. Here you can see the different amplitudes of our signal X. And then we map it with a linear function. And then we have those quantization intervals, delta, which are depicted here. So everything in this first interval will be mapped, for instance, to 0, rounded down to 0. Then everything in the next interval will be mapped to the next larger value, and so on. How exactly this is done depends on if you have a so-called mid-thread or mid-rise quantizer. Yeah, and this precise control of quantization noise is practical if you want to apply the masking threshold from our psychoacoustic model, because the step size determines the quantization noise. So we have precise control over the quantization noise if we have a uniform quantizer. Right? This quantization step size is fixed, independent of our signal x. And this quantization noise, which results from this quantization step size delta, is delta square over 12. So you can simply compute this by looking at the quantization error, and this quantization error is usually uniformly distributed between minus delta over 2 to plus delta over 2, because we assume that the likelihood of a signal within a interval is uniform. And then we can compute the expected distortion by integrating over this interval, and the result of this integration is delta square over 12. Right, so this is your average quantization noise power. And that's good to know, because in this way we have a connection between what's allowed given the masking threshold from the psychoacoustic model and what we actually produce on the noise, right? And then we can adjust the noise such that it is just below the masking threshold. Yeah, so here is a little bit more sophisticated case, the non-uniform quantization. This is used, for instance, in MPEG 1.2 layer 3 and also in MPEG 2.4 AAC. So here, instead of doing the quantization right on the signal itself, so the round here is the quantization, the round, and here then the division by this quantization step size delta q here. But now, instead of having just the signal xi itself, now we have this exponent here, this 0.75. So this is basically a little bit like a slight root. Square root would mean a factor of 0.5. No exponent would mean a 1. So this is between the square root and the linear case. So it's a slightly bent downward. A slight compression is going on here. So this function does not increase as much for large values as it does for smaller values. This basically means that we have larger quantization step sizes for larger signals, which is usually okay, because that's also how our ear perceives a signal. When we have stronger signals, then the noise can be stronger. Yeah, so we have more distortion for larger coefficients. So larger signals will be consistent here. Yeah, so as I mentioned, for uniform quantization the exponent is 1. Yeah, here you can see it in this diagram. So instead of having a straight line, now we have this slightly curved line here. So here the input is x, and you can see the output is growing less for larger x. And the output again has this uniform delta q, and that means effectively for larger x the effective quantization step size becomes larger, right, when we look at the signal itself. And that also means in the decoder we need the inverse function, which would be x to the power of 1 over 0.75. So then we have this expanding curve to compensate for the compression in the encoder. So this would be the quantizer, and this would happen in the dequantizer in the decoder. Okay, so for the quantization in our audio coder, we actually group our spectral coefficients or subbands by using a common multiplier, which we call scale factor. So this has the advantage that not every subband has its own quantization step size, because then we would need to transmit all those quantization step sizes to the decoder, which gives us a high bitrate overhead. So instead, we take groups of neighboring subbands and give them the same quantization step size. And the quantization step size is controlled by the scale factor, which is for each group. And then the groups are called scale factor bands. Yeah, so the groups are fixed, so we don't need to transmit the number of subbands in a group. They are fixed. But the scale factors we need to transmit as site information. So the scale factor and maybe additional quantization resolution in bits per sample is transmitted to the decoder. And there's one approach which uses this quantization resolution in bits per sample using a so-called block floating point approach, where we have basically something like a short floating point number, where the mantissa and the exponent have a given number of bits. And this is used in MPEG 1 or 2, layers 1 and 2, in the older A-track and in AC3. Yeah, slightly different is in the newer coders. Here we again have a group of spectral coefficients and the scale factor, and subsequently a fixed quantizer. Then this scale factor is proportional to the inverse of the quantization step size. So if we have a large scale factor, we multiply the signal by a large value. That means to the signal the quantization step size appears smaller. Yeah, and this scale factor is then the site information, and this is then used together with entropy coding. Right? So what comes out of this quantization step is an index, and this index is entropy coded because small values have much higher probabilities than larger ones, and hence we can give them shorter code words to save overall bits. Yeah, so the quantization precision is controlled by this scale factor. The larger the factor, the more precise quantization we have, but the more bits we also need. Yeah, and this is used in MPEG 1 and 2, layer 3, and also in MPEG 2 and 4 AAC, the advanced audio coder. Yeah, and here you can see how it looks like. We basically shape the noise according to the psychoacoustic model, the masking threshold. There are several subbands in each scale factor band, and they have the same step size, right? Because they have the same scale factor, which you can see here in this diagram. So the red line here is some fantasy signal. You can see here on the horizontal axis you have frequency, and those lines represent the boundaries of the subbands, right? First subband, second subband, and so on. So this is just the spectrum of one block. Remember, we have a sequence of many blocks in our audio signal, and this happens to be one block out of the long series of blocks. And in this one blocks we have samples over frequency. So here's the highest frequency, and you can see here we have the lowest energy and the highest energy at low frequencies, as is quite common for audio signals. And now imagine out of the psychoacoustic model comes this masking threshold, which tells you the sensitivity of the ear at each frequency for this given signal. And you can see it more or less follows the signal spectrum. This is actually what it indeed does. Right, and you can see it's not quite, it has a slightly different shape, but it's lower. It looks like the signal, but a bit lower. So this is the threshold at which the ear can or cannot hear noise. So we want to stay with our noise below this blue line. But now we can only approximate or we can define the noise level in those steps, right? So each step represents one scale factor band. So first scale factor band, next scale factor band, and actually they continue to grow, so they become larger. So the picture here is not very precise. What's accurate is that we approximate the masking threshold by this staircase function, right? And we need to stay below this masking threshold at every point, and that's why we have to choose the level of each of those staircases such that it just touches the masking threshold at one point, but otherwise below the masking threshold, never comes above the threshold. And in this case, all the quantization noise is inaudible. So here we have the good case, everything is inaudible, we have a perfect signal. Yeah, and often the scale factor bands are chosen to be roughly 1/2 bark, and we will also see when we talk about about psychoacoustic models what this bark means. So basically, the bark is a psychoacoustic measure which tells us how the ear behaves in bandwidth, and it basically means the bandwidth is increasing towards higher frequencies. So that's why I was mentioning that those staircases should become wider towards higher frequencies. Yeah, so here we have approximation of the masking threshold by a step function. And that means we need fewer bits for parameterization because only for each step we need to transmit the scale factor. So it's much fewer than the total number of subbands. Yeah, so usually we have the grouping of MDCT subbands into groups which cover roughly 1/2 or maybe 1 bark, which is coming up in the following lectures about psychoacoustic models. And at low frequencies, they are actually broader because bark becomes quite low, quite narrow there. Yeah, so here's an example about the scale factor quantization. So remember, everything we transmit needs to be quantized into a finite number of bits. So the MPEG AAC, for instance, uses 108 quantization steps and Huffman coding to transmit the scale factors, one for each scale factor band, as site information. And you can read more about it in the MPEG AAC standard from 1997. There is a table A1 called Scalefactor Huffman Codebook. And there you can actually see the Huffman Codebook for this quantizer. Yeah, and in the encoder it first applies a logarithmic compression function, quantizes, and then computes the difference to the previous scale factor index before applying Huffman coding. So this is also a trick because that makes the number smaller, because usually neighboring scale factors don't differ that much. So it makes sense to transmit the difference to the previous one instead of the absolute value. In the decoder, it decodes Huffman, adds the index to the previous decoded Huffman index to obtain the so-called S factor, and then applies an exponential expanding function. So here you can see it. Here we have this S factor, then we have a given fixed offset, and here we have this exponential function, which is doing the opposite of the compression in the encoder. And when you look at it, this is the only one defined in the standard, as is usual for the standard. It only defines the decoder and only gives some additional information for the encoder, informative information to the encoder, because the encoder is basically up to the producers of the software. So this is given, and then you have to think about for the encoder it makes sense to have the inverse function. Yeah, and this SF offset is given as 100, such that also negative exponents are possible here. So this gain is then multiplied with a dequantized MDCT subband value within that scale factor band. So this is then taken as a scale factor for the entire scale factor band. Yeah, so you can see it's basically the same as for the signal samples itself, just that here we have this exponent 0.25, and we have an offset here, and we take the difference to the previous scale factor index here. Yeah, okay. So when you look at the staircase approximation, that actually doesn't really look like a good approximation of an otherwise smooth curve, right? So an alternative would be a polynomial approximation of the masking threshold. This is a different way to approximate the masking threshold, to use polynomial approximation instead of a step function or scale factor bands. So the goal here is the approximation of the masking threshold as close as possible to reduce the bit demand. So basically we want to leave fewer gaps here, because all the gaps like that we had here, all those gaps are giving away possibilities to save bits. So here we could fill all those gaps with noise and reduce the bit rate, right? So here you can see there's much fewer gaps, and that means we can have reduced bitrate and still have inaudible quantization noise, meaning the same audible quality. So that's good. So you can see same signal in red, blue is the same masking threshold, and then in green you have the polynomial approximation of the masking threshold. And that means instead of transmitting the scale factor, you would here transmit the coefficients of this polynomial. Right, and you can compute this polynomial then in the decoder, and then for each subband you can actually get your individual quantization step size. And you do that by just transmitting the same number of coefficients. Just instead of for a staircase, you transmit coefficients for a polynomial. And this is used, for instance, in our ultra-low delay coder, which is a predictive coder with no subbands. And this polynomial is actually then the frequency response of a linear filter which you apply to the signal. So you can also use a linear FIR filter to the signal to do noise shaping, and then this noise shape looks like this polynomial function here. So this is actually quite practical. Yeah, so when you're done with quantization, then you do the entropy coding, which I already mentioned. So we obtain higher compression using entropy coding because we have this unequal likelihood of different quantization indices. So usually small values are much more likely than high values or high indices. Yeah, so we have an efficient representation of the symbols after quantization, for instance, using Huffman coding. So Huffman is a particular entropy coder. This is used in MPEG 1 or 2 layer 3 and in MPEG 2 or 4 AAC. Or to use arithmetic coding, this is used in MPEG 4 USAC, Universal Speech and Audio Coding. So these are the two most common entropy coding schemes, Huffman and arithmetic. So for Huffman you need tables, Huffman tables. For arithmetic you need particular formulas for the representation. Yeah, so here's an example for the Huffman code. Here you have scale factor bands, and here you have sections, and you can see here codebook numbers. So for different sections you can actually choose different codebooks, right? Because a codebook is optimized for a particular statistic, and if this statistic changes or is different in different sections, it makes sense to also transmit the codebook number as a site information, because that saves bits for the entropy coding. Yeah, so here's a typical example of the probability distribution of an audio signal. So Huffman coding uses the probability of the symbol to determine the code word typical probability distribution of audio samples are the Laplace distribution. So here you can see a plot of a Laplace function. So you can see this is the exponential function, and you can see you have e to the minus magnitude x divided by c. C is a constant typical for a certain signal. Magnitude of x, you can see here it behaves the same for positive x and the negative x. So here the net magnitude, and it becomes largest for 0. So for 0 you can have e to the minus 0 is then 1. So here you have 1 and then it decays. So that means 0 has the highest probability, and that means we give shorter code words for the more likely symbols. So for instance, for the 0, and since 0 is the most likely one, it gets the shortest code word. Right, and that on average minimizes the bit rate. Yeah, so here's an example for MPEG 2 and 4 AEC. So here we have a multidimensional 2 or 4-dimensional entropy coding. This exploits joint statistics of vectors. So this is actually one of the possibilities, for instance, used at the lowest frequencies, that we use multidimensional entropy coding. And in our Huffman coding, we have several codebooks the encoder can choose from. And the signal is in a codebook, or we use a separate escape mechanism for large quantization values. So this has the advantage that the codebook does not need to cover every possible signal value or quantization index. So since it's applied after the quantizer, we have indices, but still this index can be very large, and this is just a practical approach for codebook design. You design your codebook for the most likely values, and then if it's not in this codebook, then you have an escape mechanism, which means you need many more bits, but still you can represent this unlikely signal. And if this unlikely signal is unlikely enough, it doesn't really matter. So this is a very engineering-like approach. You design the codebooks for the most likely case, and for the unlikely case you have some escape mechanism. Yeah, and this can obtain less than 1 bit per sample with 2 or 4 dimensional vectors. So if you want to go to the lowest bit rate, it makes sense to have 2 or 4 signal values together as a vector to then quantize them together into one index. Yeah, here's an example. So here you have 2 Huffman codes for quadruples. So here 4 bits, and here you can see the corresponding code word, right? So here table A and table B, and you can see they differ in their length, and here you have actually an equal length code word. Yeah, and the encoder basically decides what code table to choose depending on the signal it sees. Remember, the encoder sees the signal and it can decide the best Huffman code table for it. And then the decoder just looks up the code table according to the index that was sent from the encoder, and then reconstructs or decodes the signal. Yeah, so this vector quantization is actually quite beneficial for very low bit rates, and it can even be a lot lower. And the problem here is only that if this group becomes too large, then it's difficult to control the quantization distortion, right? And that's problematic. Yeah, application here is, for instance, MPEG 4 TwinVQ. So TwinVQ is now absorbed basically into MPEG 4, and it's basically one of the coding tools. Yeah, so it's basically a nice concept, but it's not used too much because of this difficulty of controlling the quantization noise. But it's used extensively, for instance, in CALB speech coding that basically uses those vectors, also higher dimensional vectors, to encode speech at the lowest possible, at a very low bit rate. Yeah, and here you can see actually a diagram how basically you can take advantage of vectors. So if you have two consecutive values from a subband, say x1 and x2, or two neighboring subbands, for instance, then the individual quantization means basically you have those boxes, right? You quantize xi, x1, and you quantize x2. And that means your signal is in this box, right? But when you quantize them together, x1 and x2 as a vector, then you can change those boxes to those hexagonal shapes. And this means a denser packing of quantization spheres, and that reduces the average quantization error. And plus you can take advantage of similarity of neighboring values. So if x1 and x2 are always very similar, then you want to cover this diagonal more densely than the off-diagonal areas. Yeah, right. So today's coding schemes provide a large degree of flexibility. You have a quantization noise profile over frequency determined by the psychoacoustics. You have a trade-off audio bandwidth versus overall distortion. So actually you can say the highest frequencies you don't want to encode to save bits. You have different bitrate encoding modes. You can use optional tools. Actually, here are some examples, so-called temporal noise shaping or prediction, which we see more about later. So that's something you can still add into the mix, so to say. And you have an encoding strategy which is intelligent and part of the encoding. So actually the encoder needs to decide what codebooks to use and what tools, and that also determines the quality. And this is actually an area for specific know-how or the secrets of audio coding. Okay, yeah, I guess that should be it for today. Thank you for your attention, and then see you in the next video.